Hi again. In this video, I define exactly what's meant by Eulerian circuits and trails. We take a look at a couple examples and develop an idea for a proof. In the next video after this, we'll actually prove when a graph or multigraph, what properties of the graph guarantee, so that is necessary and sufficient conditions to have an Eulerian circuit and an Eulerian trail. So, as I mentioned in the previous video, but I'll define a little bit more concretely here. A circuit in a non-trivial connected graph. So remember, a circuit in a graph is a closed trail. And remember, a trail means that you use every edge at most once. So here we're talking about a closed walk where every edge is where each edge on the walk is used at most once, or each edge of the graph is used at most once. So a circuit that contains every edge, so necessarily then a circuit that contains every edge would involve every edge exactly once. So this is exactly the idea of Euler's, the Königsberg bridge problem, crossing each bridge exactly once. Now we sort of have the language to go with that. So, okay, so a circuit contains every edge, contains every edge of G is called an Eulerian circuit, while an open trail that contains every edge of G is an Eulerian trail. So remember, a trail, you can use each edge at most once. So if it contains every edge, then the trail contains exactly every edge of G, exactly once. And that's called an Eulerian trail. So Eulerian circuits, Eulerian trails, we're using each edge exactly once. Circuits are closed, so beginning and ending at the same vertex. Trails are open, don't have to begin and end at the same vertex. So let's look at a couple examples of this. Here I have G1 and G2. Now G1, let's examine G1 first. Notice that G1 here has this vertex of degree 1, which means as soon as we leave this vertex of degree 1, we won't be able to come back without using this edge another time. And so there is no Eulerian circuit here. And it's exactly because of this vertex of degree 1. We're going to see if we can generalize that idea. So no Eulerian circuit here. However, can we find an Eulerian trail? Can we find a route that goes from this vertex? It would have to either begin or end at this vertex, right, for an Eulerian trail, because we have to use this bridge exactly once. And if you look, let's see, can we find a trail that goes from here to some other vertex where every edge is used exactly once? So let's see, we jump over here, use that edge, and maybe we go down here, and over here. Remember, we can hit vertices more than once, but we need to use every edge exactly once for an Eulerian trail. Then we go over there, come here. Here we're going to encounter this vertex a second time. That's okay. We haven't crossed a bridge more than once. And now we go over here, and finally back down to this vertex. So we did 1, 2, 3, 4, 5, 6, 7, 8. And so we began here and ended here. And so this does have an Eulerian trail. So Eulerian trail, yes, check. So now we'll turn our attention to G2. Does this have an Eulerian trail or an Eulerian circuit? So let's see. Is there a way to do this? So you can stare at this for a while and think about it. If you want, you can pause the video and try and find one yourself. Let's try. Let's see. I'm going to try and begin and end at this vertex. Let's say we're going to try and begin and end at that vertex. And I think I can do this. So I'm going to jump over to here. Notice I wouldn't want to use, I wouldn't want to use all the edges here. I need to save one for my return journey. And then maybe I come over here. Here's where I want to be a little bit careful. But you know what I can do is I can ride all these inner. Here we have a K5 subgraph, if you can see that. I'm going to take all these sort of inner edges of the K5. Again, it's okay to repeat a vertex. As long as we don't repeat an edge, we're fine. So I took all those inner ones, and now I'm going to continue along. I want to save these edges for my return journey to get back to where I started. And then it looks like I'm going to be able to do this because now I can go doop, 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 doop. And so yes, there is an Eulerian circuit. So what I want to, so let's look at one more example where we can't find an Eulerian circuit nor an Eulerian trail. And this is the same multigraph that I showed you before. So these terms here for Eulerian circuits and Eulerian trails are exactly the same for multigraphs, where we allow the possibility of more than one edge between two vertices. That would be a multigraph. And the definitions of trails and circuits are exactly the same there, and same for Eulerian circuits and Eulerian trails. So we're asking the same question in a multigraph, and the bridges of Königsberg, the Königsberg Bridge problem, we get this multigraph and we ask the same question. And we saw the answer was no. There was no way to cross each bridge exactly once. There we didn't have the requirement that we began and ended at the same landmass, the same vertex, and so there's no Eulerian circuit, no Eulerian trail here. And remember what Euler did was he looked at each landmass. He said A would have to occur 3 times, C would have to occur twice, D would have to occur twice, B would have to occur twice. So what's really going on here is if I wanted, say, an Eulerian, if I wanted an Eulerian, let's say, if I wanted an Eulerian circuit, so one thing to notice about an Eulerian circuit is that once you have one, it doesn't matter where you begin and end. You can pick. So if we look up at this circuit here, sure, we began and ended here, but I could pick any one of these and just traverse the opposite direction. And I would still begin and end. So it doesn't matter which vertex we picked to begin and end at. That's really, we can shift the whole circuit one way or the other to begin and end at the same, any of the same vertex, any vertex we want. And so if we had an Eulerian circuit here, well, let's say we begin and end at A, for instance. Well, we have to go out of and come back into A on the circuit. And so that would mean that we would have to encounter A an even number of times, right? One for each edge that comes out of or into A. So that is if A occurs in the middle of the sequence. Not exactly. If A occurs in the middle of this sequence of this circuit, it has to come into and out of it, and so that would add 2. We would need 2 edges going into and out of A. So every time it occurs in the middle of the circuit, we need 2 edges for that. So that adds 2 to the accumulating degree. And then we also need 1 to start with, going out of A, and then 1 to come back to A. And so that's a total of an even number of times, an even number of bridges that would have to be going into and out of A. But A has an odd number of edges, and so this would be impossible. This is one way to see it. It's just the fact that A has an odd number of bridges means we couldn't have an Eulerian circuit. So our idea is to generalize this to all graphs and prove what properties of the graph guarantee an Eulerian circuit, what properties guarantee an Eulerian trail. So if we jump up to this Eulerian circuit, this example we did before, you'll notice that each vertex has even degree. This makes sense for an Eulerian circuit. It's not too hard to see that this is a necessary condition. If we have a circuit, every vertex has to have an edge coming into and out of it. So every time it occurs in the middle of it, we get 2. We need 2 edges for it. So that's it has to have even degree if it's in the middle, and if it's at the beginning and end, well, then we get 1 for the beginning, 1 for the end, so again, an even degree. So it's not too hard to see that if we have an Eulerian circuit, every vertex has to have even degree. So that's a necessary condition. So we would wonder if there is a sufficient condition, if that's also a sufficient condition. So let me maybe write that out. So necessary condition for Eulerian circuit. Every vertex must have even degree. That's not too hard to see. So now we wonder, is this also sufficient? And then over here we have the Eulerian trail. Now notice here we have some vertices of odd degree, in particular this vertex and this vertex, the ones we began and ended at, each have odd degree. So again, it's not too hard to see the sufficient condition here, which is that if we have exactly 2 vertices of odd degree, then we should be able to find an Eulerian trail that starts and ends at those vertices of odd degree. And again, the question becomes, is this condition also sufficient? We know it's necessary that this should have to occur. Is it also sufficient? And in each case, actually, it turns out these are necessary and sufficient conditions. And so this problem is pretty easily solved. In the next video, we'll take a look at a proof where we'll go through both the necessary, the need and sufficiency for each of those conditions in each case. All right, I'll see you there.